another model, which are simplicial categories. Yeah, from the name you can actually guess what they will be, but let me go through it properly. So simplicial categories are going, by simplicial categories we will mean categories enriched over simplicial sets. So firstly, let me remind you or tell you what are enriched categories. Is it okay? Okay, so in order to define an enriched category, we should start from a monoidal category. So let V times and I be a monoidal category. Then the V category C, or in other words, a category enriched over V consists of the following data. That's pretty annoying. Okay, maybe this one will work. Okay, so of course, if we have a category, we need to have a collection of objects. And for every pair of objects, X and Y, we have an object home underlined from X to Y, and this object is supposed to be in our category V. And then for every triple of objects, X, Y, and Z, we have a morphism C, X, Y, Z, going from home C, X, Y, cross home tensor C, Y, Z to home in C of X to Z. And the fourth piece is for every object X, we have a morphism EX from I to home in C from X to X. This is supposed to be an identity morphism. And so we have these four pieces of data, and we have some coherence axioms. I will not list them, but okay, I assume that everybody probably saw here the definition of enriched category. So just to point out, the idea is as follows, that for example, if we think about abelian groups, and we have homomorphisms from one abelian group to other abelian group, we can give it a structure of abelian group. So this is kind of saying that abelian groups are enriched over themselves. If, well, some other examples, if we have topological spaces, continuous maps from topological spaces to topological spaces can be given probably in some, we need to put some assumptions here, but they can be made into a topological space. So this is saying that topological spaces are enriched over topological spaces. And well, every category is enriched over sets, just by definition. So objects are clear. This part is telling me that for every pair of objects, I'm giving to the home set of this object some more structure, like topology or abelian group or whatever, or simplicial structure in our case. This part is telling me how I am supposed to compose morphisms, these kind of enriched morphisms, and well, this is the identity. And then coherence axioms are telling me how, well, something about associativity of composition morphism, and yes, how it commutes with identity, stuff like this. Okay, so a definition, no, oh, sorry, definition not yet. So first we should say that simplicial sets are, or maybe let's write it as is a monodial category. Well, with respect to the simplest product, so with respect to the Cartesian product, and the unit is given just by one vertex. So having this, we can talk about categories enriched over simplicial sets, and this will be definition, our definition of a simplicial category. Now, there is a disambiguation here, because by simplicial category, we could mean something else, namely we take a category of all categories or category of all small categories, and then we might say that a simplicial category is a simplicial object in this category. And in full generality, these two notions are not the same, but there is a connection. So yes, if I take fixed objects, yes, if I fixed an object of my category, then simplicial object on this fixed set of objects will coincide with what simplicial category, right? Yeah, all simplicial categories on these structures on this fixed set of objects. Okay, so this is a definition which we'll work with, and firstly we'll need to define a little bit of more notions. So similarly as, no, I cannot say this, but here, if we have a simplicial category, then we can define its underlying category. C is the category consisting of So objects of C are defined to be objects of C bullet, and well, morphisms in our category C from object X to Y are defined to be home, enriched home in C bullet from X to Y, but this is a simplicial set, so I can take its vertices. And this will give me just an honest category. Okay. One thing I should say here is that we can actually, 0 is not very special here. We can do this construction with any n. So this would be like an, I don't know how to say it, nth layer of a simplicial category. But for our purposes, we will just use this underlying category with this definition. Okay, so what is an example, kind of motivating example of a simplicial category? Well, one of motivating examples, of course, a part of simplicial sets, topological spaces. So in topological spaces, we can define. Yes? No, so the composition is given by this map. Well, it depends on your structure. So this is not, this is part of the structure which you are giving. Yes. Yes, so we have, I mean, so let's, how does it work with sets? So sets are also, is also a monoidal category with a Cartesian product, right? So, but then if you have home set here and home set here, then you don't have any kind of pre-described information how the composition works. A composition is a map from home set on X and Y cross home set from Y to Z to home set from X to Z, right? So that's basically all the information which you have.
Say what it is in the sense that you have mapping spaces everywhere, right? There are simplicial sets, and how do you get from a pair of mappings maps a map from X to Z, right? In specific,
yeah, but you need
in general simplicial category, it's a definition just from.
Yeah, I mean you cannot. You.
What do you mean? You're asking if there's a simplicial sets. Category of simplicial sets. Okay. Yes. Or maybe how do you see? So the
okay.
structure there is the Cartesian. Okay, I think you're asking this, right? Monoid structure. We're asking. Oh, I see that you have to.
Yes, yes. So you don't have it like, I mean, this is a part of the structure. In order to say that this is a simplicial category, I need not only to say that home sets can be given a structure of a simplicial set, but I need all of this data, right? So I haven't listed coherence axioms, but then if I have, so I have simplicial sets as home sets, and then if I want to compose morphisms, I need to give this map. So yes.
Is the fact that one doesn't build into the simplicial category definition?
Yes, yes, it does. Because, okay, so what is the idea behind infinity one categories? The idea is that we would like to model homotopy in some broad sense. So what are categories where we know how homotopy works? Topological spaces, simplicial sets, probably chain complexes. But then, so we have one tool which are model categories, but well, then we have the problem that we can have a couple of model structures on a category. Here, we have different approach. So we are saying something like, we know how homotopy works in topological spaces. So let's model homotopy by topological spaces. So what should be infinity one category? Infinity one category should be something which is enriched over topological spaces. But topological spaces are not really well behaved for computation, so why not using locally can complexes instead? So categories which are enriched over simplicial sets such that every home set is actually a can complex. And then in this information, if you have two objects, x and y, you have all information built in because you have morphisms, you have homotopies between morphisms, and then you have this coherency conditions which are saying that, okay, we have homotopies between homotopies, and so on and so forth. So
Describing a special case of simplification will be the ones that comes from the special category itself has no built-in thing about ones.
no, it does, because I can, what is this in this map? What is this in simplicial category? So I'm taking what is a product of Cartesian product of simplicial set. I will just have here one simplex times one simplex, and I will have two one simplices sent to some one simplex. Yes. Yes. No.
The definition of simplification category
No, no.
the underlying category. I mean, the definition is already finished.
Yes, the definition is finished here. Yeah. Oh, sorry. Maybe I should write one more thing. A morphism in V. So maybe this will resolve the problem. And this is also morphism in V. So then we have all of the information because, well, home sets are supposed to have simplicial structure, and then these are morphisms in our category, in simplicial sets in our case. So then you have morphisms between zero simplices, one simplice, and so forth, so on and so forth. But you have also all of the simplicial data, like phase and the degeneracy maps. Is it okay? Or
yes, I see that. So suppose C V is the simplicial set category.
yes?
Find the home
Yes. No, so here, this is other definition. I'm just saying that if I have a simplically enriched category, then I have some underlying category on it, right? So I don't know. Let's take simplicial sets enriched over simplicial sets. So yes, how does it work when you define category of simplicial sets? First, you define what is a simplicial map. So which is just map coinciding with, commuting with the simplicial operators, and then you can impose on this set some more structure. Well, not exactly on this set. You can just give a definition of simplicial sets of morphisms, right? So yes, so we have more structure in the category of simplicial sets on the space of maps between x and y, but there is also underlying category which are just simplicial maps.
Can we say the example?
Yes. Okay, so I'm going to give an example. So example is that for topological spaces, we can define the simplicial set. So Okay, so this is how topological spaces are enriched for x and y in top. How topological spaces are enriched over simplicial sets. In particular, there is a very well-known construction. So we have that home from a point to y. This is a singular simplicial complex of y. Is it okay? Okay, so as I said, the idea of having infinity one categories is to have in home spaces to have built all of the information also about homotopies and coherent homotopies. So firstly, let's say what is the homotopy in the simplicial category. So if we have two morphisms, in category C, in a simplicial category C, so let's say that the underlying category then a homotopy from F to G is an edge H in home enriched in C from X to Y1 such that D0 of H is equal to G and D1 of H is equal to F. So if we have a simplicial category, we actually also have a notion of a homotopy between two morphisms. And just I should make a remark here why a simplicial category is a model for infinity one category. So what do we mean by infinity one category is that we have for every two spaces we have notions of n morphisms for all n's and all morphisms all n morphisms for n greater or equal than 1 should be invertible in some sense. So this is well what is happening once again in topological spaces, right? If I have homotopy from F to G, I also have a homotopy from G to F. And here, if we have a simplicial category, which is locally Can complex, then I also have this property, because if I have two maps, and I have homotopy between them, what I can do is I can degenerate F to have identity of F on this edge, and what I get is an inner horn. And because I'm in a Can complex, I can fill this horn, and in particular, I will have this guy over here. So in this sense, H is invertible. There exists some homotopy in other direction. Yes?
Yeah, we know that singular is Can complex, right? That's nice, like it shows that the set away, but in general, this one home topological space, the home is Can complex in general for every topological space.
I don't know, but it should be, right? I mean,
Yeah, I'm not sure. Yeah. Because in this case, when we take, we know that singular, yeah, it's right. I think yes, yeah, we can, because also the proof that singular is easy the same way.
yes, I would say so, because, well, as I understand, Kant complexes are topological spaces, right? In a sense. So here, what I'm having is okay, I see the question. Okay, I don't know the answer, but I think that it should be true. Okay. So because of this remark, I should make one more definition. So if we have C bullet a simplicial category, so we say that C bullet is locally Can if home in C bullet between any two objects is a Can complex for X and Y in C. So here we should have that locally Can simplicial categories are models for infinity one categories, exactly because of the thing which I said a moment ago in the remark. That is, starting from degree 1, we can invert all one morphisms. Okay, and if we have a locally Can category, okay, so I should probably say one more thing here. The problem with simplicial sets and why Can simplicial sets are nice is that if I have a homotopy, if I have three simplicial maps between arbitrary simplicial sets, then the homotopy might not necessarily be transitive. And in order for it to be transitive, I need my simplicial set, probably the target should be Can. Right? So this is the problem, and this is why we need locally Can condition. Okay, so here a remark is that if C bullet is a simplicial category, then the following are equivalent. So firstly, there is a homotopy from F to G, and secondly, F and G belong to the same connected component of home. Yes. Okay. Okay, so here I am now in a position to define the homotopy category of a simplicial category. Yeah, so this is what Aziz asked, and I think this should be true. Mm-hmm. Yes. Mm-hmm. Mm-hmm. Yes. Also, there is also a heuristics behind it, so the topological spaces should be a kind of the example of an infinity one category. So this has to be true. Okay, so having all of this, we can define the homotopy category of simplicial category C is an ordinary category. So this is the same pattern which we had in with quasi-categories. Is an ordinary category whole C-bullet with, so firstly, the same objects, and secondly, the morphisms in the homotopy category of C-bullet between objects x and y are given just as connected components of the hom set x, y. Okay. So here I will not write it, but we can. So now, similarly as in model categories, in the model categories, we defined a homotopy category and we defined a functor from a model category to its homotopy category. We can do similar thing here. We can also define a functor from C bullet to its okay. I should probably say something more. I should probably say what are simplicial functors. So this is what I should start with. Okay. Yes. But also here I wanted to make another remark, and this is probably which we'll see in Aziz's talk. So Aziz will talk about Dwyer-Kahn equivalences, Dwyer-Kahn localizations, and part of it is if we have a model category, we should have infinity one category associated to it. And here there is a slight disambiguation. So if we, for example, discuss topological spaces with Quillen model structure, we know that its homotopy category is a homotopy category of CW complexes, is a category of CW complexes. And what is homotopy category of simplicial sets with Quillen model structure? These are Kahn complexes. But now if we think about topological spaces as a homotopy, as a simplicial category, then its homotopy category will contain all topological spaces instead of only CW complexes. So we'll see, I think, this connection as is stock, I hope. Okay.
sorry, maybe I didn't understand. Sorry. Yeah. No, but of course, yeah, I need this. Yeah, this of course.
Yes.
Yeah. We show that it's enriched, that the same.
Yeah, exactly.
The model category, yeah, of course.
Okay, so small remark here why having locally Kahn simplicial category is important. So if we have a simplicial category, and f and g from x to y are two morphisms in the underlying category C, then the following are equivalent. So the first thing is that the morphisms F and G represent the same morphism in the homotopy category. So in other words, they belong to the same connected component. And B, there exists a sequence of morphisms F equal F0 up to Fn equal G in Hom Cxy such that for I between 1 and 1 there exists a homotopy either from F I minus 1 to Fi or from Fi to Fi minus 1. So this is the problem when we don't have Can complex.
You have to take the generated.
Yes, yes, exactly. So let me just let me finish the remark. The remark is saying that if C is locally Can, then we can replace B by the condition C. There exists a homotopy from F to G. Okay. So last two things in kind of in a definitions area is what are simplicial functors So if you have two categories, two simplicial categories, C bullet and D bullet, then a simplicial functor from C bullet to D bullet, so let's call it F. So it is supposed just to be an enriched functor, so it consists of the following data. That for every object X in C, there is an object, I mean, we assign an object F of X in D, and for every pair of objects, X and Y in C bullet, a map of simplicial sets from Hom C on X, Y to Hom D from Fx to Fy. And here, of course, plus coherence axioms. Okay, so what I wanted to say here is that if we have a homotopy category of a simplicial category, then similarly as in model categories, we can define a simplicial functor from simplicial category cibulet to ordinary category ho cibulet. Of course, now what I mean by, well, a functor from simplicial category to ordinary category, we are taking a constant simplicial set as on pi 0 as okay. No, we think about homotopy category of cibulet as a simplicial category where every hom set is a constant simplicial set on pi 0 of hom cxy. And then we can define the simplicial functor on objects just by identity, and we are sending a simplex to its connected component.
But every category you can think as simplicial. Like we just take it as generic.
Yeah.
But every set as simplicial set. What you do, right?
Yes, I think so. Okay, so are there any questions so far? Yes, I mean, this is not even special, it is just particular instance of this. Okay, so now let's move to homotopy theory. So now I will move to discussion of Bergner model structure. Okay, so in this idea of infinity one categories, we have a couple of models. So we already discussed quasi-categories. We are now discussing simplicial categories. We will discuss complete single spaces. And now it would be nice if these models somehow coincide. So of course, because we are doing homotopy theory, models of homotopy will coincide up to homotopy. And what is it supposed to mean? Well, we'll construct Quillen equivalences with between appropriate model structures. So last week, I think I gave a model, I defined Joyal model structure, which was supposed to be model structure on simplicial sets, kind of seeing the quasi-categories. Now I will define a Bergner model structure, which is a model structure on a category of small simplicial categories. And then in a couple of talks, we'll construct a Quillen equivalence between these two models. Okay. So the Bergner model structure is on the category of small simplicial categories. Now, what are weak equivalences? Just to remind, if I want to define a model category on the nose, I will later on give a simpler way of defining model categories. But if I define model category, a priori, I should have three classes of maps distinguished, which are weak equivalences, fibrations, and cofibrations. Actually, because of properties of these maps, I can define some of the data is kind of redundant. I can define either weak equivalences and fibrations or cofibrations, because the others will be defined as a maps having the left or right lifting property up to acyclic, respectively, fibrations or cofibrations. So here we'll give just weak equivalences and fibrations. So what are weak equivalences? So these are maps. So simplicial functors from F C bullet to D bullet, such that firstly I need to have that F induces a weak homotopy equivalence between the home sets for any x and y in C bullet. And secondly, I need to have that F is essentially surjective, which means that any object of D is equivalent to, is it visible if I write here?
Yes, fine.
Is equivalent to f of x, small f of x, for some x in C bullet. And here by equivalent, I mean that if I pass to the homotopy category, then yes, what I should say, so if I take an object in D, I should have map in y directions or other from D to f of x, such that after passing to the homotopy category, this map will become an equivalence. And we can express the two in a simpler way. Because if one is satisfied, then we can express the second condition as two prime that homotopy category of C, so this will be induced functor to homotopy category of D is equivalence of categories. What about? In part two? No, yes, in a sense. So once again, in part two, I mean that if I take an object of D, if I take object D of D, there must exist some f of x and a map from one way or the other, such that after passing to the homotopy category, it will become an equivalence. So yes, in a sense, homotopy equivalence. Isomorphism. Yes. Okay, so I defined weak equivalences and fibrations. Say again, sorry? Well, I mean, I'm pretty sure that there is such notion.
I'm going to ask, is this equivalent to having functors in both directions so that compositions are
Uh,
I think is a definition just in general, but defined in coordinate. Yeah, I think that
Without enriched, this would be called these two conditions fall into two categories. What direction?
it's not true that you have this something weaker, I think. Weaker. Maybe you don't have
There's a nature.
Yeah.
weaker than not true then you have.
So usually when you have a homotopy category, so then when we think about what should mean simplicial categories which are equivalent up to homotopy, usually that means that you can connect them by a zigzag of weak equivalences, so that you have one category here, other category here, and they will be equivalent in a homotopy category if you will have, say, C1, C2, C3, and so on and so forth, and, well, C bullet 1 prime, I don't know, C2 prime, and so on, and you will have a zigzag of weak equivalences which will connect the both categories. I don't know whether this is as what you asked, but it is more or less connected. It's not that if I have weakly equivalent simplicial categories, or in general weakly equivalent objects, then on the nose there will be inverse of a map joining them, right? No.
Yeah, exactly.
So it's like in topological spaces. In topological spaces, if you have weak homotopy equivalence, a priori, you don't have any inverse of this. And this was other definition of a homotopy category of a model category. Then,
Yeah, I see. It's not here anymore.
Yeah, this is that.
Okay.
My battery is also that.
Okay. I can use my battery. Yeah.
okay, yes. Then if you
maybe here also localization, like if you are five trans your object.
no, I was about to say something else. That how you define homotopy category, you take weak equivalences and you kind of artificially add inverses to these weak equivalences, and this is how we define homotopy category. So in homotopy category, there will be a map in other direction, but it doesn't mean that yes, there will be a map, and I should probably stop here my sentence. Okay. So continuing the fibrations, so a map, well, a simplicial functor f from C bullet to D bullet, such that firstly f induces a Kan fibration from home in C bullet x, y to home D bullet fx to fy. And secondly, I think that this condition is called isofibration, is that any equivalence alpha from f of x to y in the bullet can be lifted to an equivalence
again you use a capital letters, it's can confuse people. Because
Yes.
here the capital is small.
Yes, here is f small and small f.
No, and also the bottom small.
Ah, okay, sorry. Can be lifted to an equivalence. So some a from x to some x prime. And by lifted to an equivalence, I mean there is a map a from x to x prime such that f of a is equal to alpha. Okay, so this is how we define a Bergner model structure.
And also change to prime if one is given.
I don't know, but just a moment. Can you change 2 to prime to some other simpler condition if one is satisfied? Yeah, I don't know. But
Maybe Cihan may be like something in the homotopy category like this.
Yeah.
yeah, this is
to be subjective, maybe some like, because what do you mean by here the equivalence you define, like there is a homotopy.
Yeah. Okay, I'm now thinking. Okay, what should happen? So we will know that this. So if I include empty simplicial set, the 1-point simplicial set, this will be a trivial cofibration. Then I can send it to. Oh, but oh, trivial, yes. I can send it to home d x y. Ah, but this is not inner horn, or is it? Yes, what I wanted to say is that because this is confibration, if we had inner horn over here, there probably would be some condition like this because we would have some lifting property over here, right?
But why you talk this? Because you say that there is in D, right? Homotopy, maybe you have to take then homotopy like delta 1. You know what I mean? Like you have to take here instead of point.
Yes.
Take delta 1, which is the homotopy that makes the equivalence of alpha. And then maybe you can do this. And then here it's just.
Ah, but okay, inner horn in this case will be just 1 point, right?
Yeah. But it's okay for this case. The definition of also work for this case. So the 1 point it's alpha. Alpha.
Yes.
Alpha.
No, but you need alpha in the bottom. So this is alpha.
No, the homotopy alpha is just this is the homotopy for alpha.
Ah, no, sorry, this doesn't make sense. I should have here. No, so I don't think. Okay, because alpha a priori belongs to home the bullet from fx to y, and this is right. This is where alpha belongs, and this statement is telling me that firstly.
Sorry, but maybe not alpha. I mean here the homotopy that connected in alpha because it's equivalent alpha. If you want alpha, you have to put point there instead of delta 1.
Yes, but okay, forget about it right now. So what I'm saying is that alpha belongs here. And before doing any kind of these diagrams, you need to at least know that there is some object which will by f hit alpha over here.
Maybe you also need to combine these things.
Yeah, exactly.
But anyway,
So maybe it's not really the case. Okay, so now I defined a model category. So now I will proceed to kind of technical stuff, which will be proving that this is model category, that this is model structure. But in order to do this, I will do a huge aside on covalently generated model categories.
Igor, I have a question, but I didn't understand here the data what you wrote. D after D, can you read this after D?
This
Oh, yeah,
cannot
can be
lifted.
lifted.
Okay, so covalently generated model categories. Here the idea is that sometimes we can simplify the model structure. Well, not simplify, but simplify the proof that the model structure is indeed a model structure. And we can generate cofibrations, all cofibrations as a push-outs, as a retracts of push-outs of coproducts in our category of some generating cofibrations. So let me make it precise and give you some idea how it should work. Okay, so firstly, a definition. Let C be a category and I be a collection of arrows in C. Then we call a diagram Z0 to Z1 to Z, possibly infinite, an I diagram if all maps from Zk to Zk plus 1 are push-outs of elements of I, then yes, we assume that C has sequential colimits so we can define Z to be the colimit over K of Zk. Now there is a definition that an object X in C is I small if for any I diagram well, Z0 to Z1 blah blah blah, the following map, the map colimit of homes from X to Zk to home XZ is a bijection. Okay, so when we prepared this seminar, I really hope that we will avoid small objects argument and this discussion, but it turned out that we cannot do this. But right now, what I'm doing is I'm following Professor Hinich's notes, and this idea for me is much easier because, in general, this kind of small objects are defined for any ordinals. But here, I think that we are restricting ourselves just to countable ordinals, and we explicitly saying what are small objects. Now, what this definition is telling me, let's take a look on an example. So from the literature, I know that topological spaces with Kulian model structure is a cofibrantly generated model category. So let C be topological spaces, and I, in our case, will be set of maps of the form Sn into the n. So here what I'm doing is over n greater or equal than 0. Elements of I. So every map over here is a push out of the diagram where here I have this map is in I, and this is push out. Okay, let me give you an example because I think that example will really help to clarify this idea. So let me C be topological spaces and I to be maps, to be inclusions of a sphere into the disk. Here plus I want also disjoint unions of these arrows. So in other words, I'm taking a disjoint union of spheres sent to the disjoint union of disks. Now, what does it mean then an object would be X small? So firstly, what is an I diagram? I'm starting with a topological space. So Z0 is just an arbitrary topological space. But now, here, what I'm having is, on the first step, maybe I should make it bigger, so I will move over there. In the first step, what am I supposed to do? Yes, so here I'm having some disjoint union of spheres included in a disjoint union of disks. Right? And this map is supposed to be a push out of this diagram. So really, I'm starting with a topological space and I'm adding cells to it. Right? And by the definition, every step of this will have the same form. So what is an I diagram in our case? This is a diagram in which in every step I'm adding cells to a topological space. Now, what will be object Z in our case? This will be a relative cell complex. So a cell complex, but obtained, well, so 0 cells of my cell complex is Z0 plus additional 0 cells. And then I'm adding cells of higher dimensions. Now, what this condition of being I small is telling me, so if I need to have a bijection over here, so that means in my case here I am taking a colimit from X to Z. How do you usually, let's write it like this. sorry, zk. So this one over here is the kth skeleton of z, right? And if this map is a bijection, what does it tell me? Firstly, this map is surjective. So if I have a map from, every time I have a map from x to z, it has to start at some finite, it has to start at some finite skeleton, right? And secondly, if I have a map here, it will have unique lift over here. So what are small objects in the topological spaces? Finite CW complexes. And I think this is well, this is an idea behind all of these small objects argument.
Finite CW complex is the I small complex. X, you mean I small complex, right?
Yes, X here is small object.
So you see that it's finite. Sorry.
Okay. Why is that so?
Compact ones will go into the finite skeleton.
I mean, you think that I need this restriction here? Because okay, so maybe I was thinking kind of about up to homotopy, but for any yes, you're right. Yes. Okay. Yes. So that's a little bit weaker than I said. So okay, right, the small objects in topological spaces will be compact spaces. Okay. All right. So this is an example of for this definition. And now, yes, I still have 20 minutes. So a definition of what is a cofibrantly generated model category. So a model category is cofibrantly generated if there are two sets I and J of morphisms in C such that fibrations of C are precisely the arrows satisfying the right lifting property with respect to J. So do you want me to write explicitly what does it mean? Okay. Okay. So then for any alpha from x to y in I, I, the source x is I small, and the third condition is that maps which has right lifting property with respect to maps in J. And the third condition is same for morphisms in J. In other words, whenever I have a morphism in J, its domain should be J small. And once again, our example of a cofibrantly generated model category is topological spaces with Quillen model structure. So just here, a priori, I have more model structure on topological spaces because here we have, in the Quillen model structure, we are choosing fibrations to be self-fibrations, but there is also model structure where, so yes, what are self-fibrations? These are maps which have a right lifting property with respect to CW complexes. But we can take also fibrations to be maps which have right lifting property with respect to any homotopy, I think, something like this. Yes, just with which have homotopy lifting property. And this will give us different model structure. Okay, anyway, so top Quillen is a model cofibrantly generated model structure with I, the set which I gave a moment ago, so inclusions of spheres in disks, and J, well, we would kind of say these are, I don't know, adding whiskers or something, because these are inclusions of dn of disks in cylinders. And how we obtain, well, if we have, if we can guess that our model category will be cofibrantly generated, then it will simplify things a bit. And now we should say, what are the conditions for I and J to generate a model category?
You don't see the relation between G and I. There is no relation. What is the relation between G and I? These two.
So far, there is none, right?
I don't see in the.
No, these are not axioms. I mean, this is just definition of, yes. No, so a priori, at least, well, but okay, these lecture notes are probably correct. So there is no further assumptions on this.
These are the
Okay, so here, if you have cofibrantly generated model category, these are called generating cofibrations, and these are generating trivial cofibrations. And yeah, I was about to list the theorem. If you have a cofibrantly generated model category, then you know, and you have these sets I and J, this will contain all of the information about cofibrations and fibrations, because cofibrations will be retracts of transfinite composition of pushouts of maps of I. So in topological spaces, for example, cofibrations will be relative cell retracts of relative cell complexes. In other words, a part of retracts, I'm including a topological space in a relative cell complex, so I'm adding cells to it. And then, of course, retracts of these maps will be also cofibrations. And also I have informations about fibrations included in here, because fibrations will be all maps which has a right lifting property with respect to J. So the name comes from the fact that these two sets will generate as a whole model structure. Plus, of course, weak equivalences. So we need also to say something about weak equivalences. So this theorem makes it precise. So let's see, has small colimits and small limits. Let W be a subcategory of and I, j, two sets of arrows. Okay, so assume that firstly W contains all isomorphisms. Satisfies 2 out of 3 property. And is closed under retracts. Okay, further on, domains of I and J. Well, here I'm messing terminology a bit. Domains are the same thing as sources. Of I and J are I, J small respectively. Colimits of J diagrams are in W intersected with LLP on R, LP on J. So here answer I. So here what I mean is that RLP on I are maps which have right lifting property with respect to I. Right, so here once again we should keep in mind the idea behind all of this. I are supposed to be to generate as all of the cofibrations. So maps with respect to with right lifting property with respect to I should be all acyclic fibrations. Now, what are maps which have left lifting property with respect to acyclic fibrations? This will be cofibrations. So this is supposed to describe all cofibrations to me, and colimits of J diagrams, these are supposed to be trivial generated cofibrations, are supposed to be also weak equivalences, and this is the connection you asked about. And finally, maps which have right lifting property with respect to I are maps which have right lifting property with respect to J intersected with W. So these are assumptions, and if we have all of this, then C has a model structure with weak equivalences defined as W, and fibrations defined as maps with right lifting property on J. Okay, and here this is not, I can also show, I mean, okay, not I, it can also be shown that cofibrations in such case are, as I said, this will be retracts, firstly, of push-outs of diagrams, of colimits of diagrams in I. Yes. So I think this is no, but okay, this is from Hinich, but he is, I think, citing it from Hovey. Yes, but I like this setup because I can see what is happening here, more or less. Okay, so very good. I have 5 minutes, so all of this huge aside was just to say that Bergner model structure is cofibrantly generated. So let me just give you generating cofibrations. And yes, I will stop on this because we have just 5 minutes. So for simplicial sets, for a simplicial set S, we will denote by 1 on S the simplicial category with two objects (0 and 1) and morphisms so morphisms from 0 to 0 are the same thing as morphisms from 1 to 1, and we will have only the identity here. So of course here I mean that we have a simplicial set generated by 1 point. Home from 1 to 0 will be empty, and home from 0 to 1 is equal to S. Okay. So let me at least list the generating stuff. So generating cofibrations so by this I mean the set I are of the following form. So 1 on a boundary on a simplicial sphere, inclusion of this into 1 on the n simplex, and inclusion of an empty simplicial category to a 1-point simplicial category. So these are generating cofibrations. And generating, so we are saying this should be trivial. So generating trivial cofibrations yes? Sorry, say again? So these are functors, simplicial functors. So here I have simplicial category with 2 points and a home set. Yes, as here is the simplicial sphere, and here, well, this will be inclusion on the home set. This will be inclusion to the. Yes. And what are generating acyclic cofibrations? So firstly, I have the inner horns, not inner horns, horns. So this will be for all horns, sorry, not only inner. And also this will be this will require a little bit of writing. So I have a map from a single point to J. Well, it's not a good name, is it? I don't know, maybe A, where A belongs to the set of representatives of isomorphism classes of simplicial categories with two objects zero and one, and countably many simplices in each, well, I will write home set. Of course, by home set, I mean here a simplicial set, and which are required to be weakly contractible plus the map 0, 1 to A is assumed to be a cofibration in set 0, 1. Okay, so a quick explanation for the last point because it is kind of wordy. So here, what are these isomorphism classes? So A basically should have two objects, 0 and 1. So this is similar to this, but I can have more simplices here, here, and here. However, in every dimension I should have, no, in total I should have countably many simplices. Objects, home sets should be weakly contractible. And the last statement is saying me that inclusion of the category on 0, 1, so I have just 0, 1 and identities into A, should be a cofibration in this category. Sorry, this is not set, this is cut. So what is this? These are all simplicial categories with two objects, 0 and 1. And what is the model structure? It is defined more or less in the same, not more or less, it is defined in the same way as the Bergner model structure without these essential surjectivity conditions. Okay, so, but it's, yes. So thank you very much. I hope everything was clear. Yes. So, are there any questions? Yes. No, in Aziz's talk, we'll see how to pass from simplicial categories to quasi-categories later on in homotopy coherent nerve.
Oh,
Mm-hmm.